Hi, this is Trev and welcome to my vlog. Welcome to part 3 in my mini-series on MIG welding. In part 1 I showed you how to match the wire speed with the voltage, and in part 2 I showed you how to do some plug welds, some butt welds, and the difference between MIG and TIG and many other things besides. And in part 3, this part I'll be talking about the different wire thicknesses, why we need shielding gas, and why it's worth fitting a flow meter. I'm also going to be talking about the difference between volts and amps, and why there is no amperage setting on a MIG welder. But before I get started, just like to say huge thanks to David, a viewer, who sent me this t-shirt. Thank you very much, David. That's exceptionally generous and thoughtful of you, because of course I talked about the great Ron Cavall in part 2. So anyway, let's crack on with part 3. The composition of the gas that I use is actually called 5% CO2 argon, which is 95% argon gas, 5% CO2. Some argon mixes actually put a little splash of oxygen in there, and I believe that's to do with being able to create a spray transfer. So there's a spray transfer mode, and I believe that aids that little bit of oxygen. Now this comes to me fully recharged with 3,000 pounds per square inch of pressure in it. We don't need that, we only need a whisper of gas when we're MIG welding, so it has to have a regulator which is bolted to it. So the bottle valve open to tell you what's in the bottle, and the regulator valve, you need to wind that clockwise to turn up the flow. So as I turn this clockwise, you'll see the needle rising up, like I said, around 6 litres per minute. It's kind of where I weld normally. Maybe doing something a bit thicker, you could rise it to about 8. I mean, people have debates about these kinds of things all the time, but I've got by with these settings myself quite substantially well. Now, something I want to discuss is I've actually got a flow meter on this gauge, and for very good reasons. I'll explain why. So this is the gas flow meter as bought from Artec Welding about a month ago. I think I paid around 14 to 15 pounds for it, next day delivery. So let's talk about how this flow meter works, how you set it up. So I've turned the welding bottle on, the welding bottle's on. Now what I would typically have done is I would have typically set the flow on the gauge to around about, I don't know, 10, 12 litres per minute, something like that, and then used the flow meter to regulate that pressure. What I have found setting it up this way is that you get a big purge then of gas when you first pull the trigger back. So you get this huge burst of gas, and then it drops right down to where it should be. So I've kind of learnt through trial and error really that what I do is I just have this wound flat out. So this is wide open as far as it'll go, and then what I do is I then use the regulator valve to control the flow on the actual flow meter, and this gives me a pretty good accurate indication as to what the flow is of gas going to the torch without having this residual build-up which pushes this great big purge out to start with. I'll show you what I mean by setting it up using this valve. I have to turn the welder on first. Got the welder turned on. I've got the trigger pulled back as well. So what I'll do now is I'll turn the flow up on here. So I'll turn it up until the centre of that ball bearing is roughly at around 6 litres per minute. When I release the trigger, it drop back down again. Press the trigger, back up, back down. Now what I'll do is I'll put the torch right next to the microphone on the camera so you can hear the gas flow. I'll show you the difference setting it up the other way so you can hear the purge on the second way. So this is how I've got it set for now. So let's give it 10 litres per minute. And then we'll use the gas flow meter as another regulator, if you know what I'm trying to say. I'll then adjust this up Much more unstable now. Okay. So now let's have a listen to the difference. So I'll hold the torch up to the microphone, see if you can hear the difference. You can actually see the pressure affecting this pipe as well. Look. Okay, so that's what I've learned anyway. Wind that flat out. So that's opened out, flat out. Pull back the trigger and then use this to set the gas flow. Then you don't get that residual build-up in the pipe. See, the pipe's much more stable, it's not twisting itself into knots now, and we've got a nice even sounding gas flow. The next thing I'll show you is a comparison between the two so that we can see any inaccuracies. So I'll set the flow gauge to 6 litres per minute on the actual regulator gauge. So pull back the trigger and let's set the gas to about, well, I would have said that's around about 6 litres per minute. And let's see what we're actually drawing off now on the flow meter. The flow meter valve is wide open, so I'll pull back the trigger now and we'll see where we're actually at. So we're looking at around about 10 litres per minute on the flow meter now, with this gauge set to 6. So we're looking at a discrepancy of around about 4 litres per minute, which is quite substantial really. I've got this spare argon regulator. I've just taken off the back of the flow side just to show you what the gauge looks like inside. Now all these gauges work pretty much the same way. The gas pressure goes up into the gauge and round into this copper tube. Now this copper tube, when it gets full up of gas, it tries to straighten out, and when it tries to straighten out, it moves upwards like that and operates this mechanism that turns the needle on the front. So it's fairly crude. Now with regards to telling you how much is in the bottle, it gives you a pretty good indication as to how much is in the bottle when you're going to run out. You're pretty much fairly safe with that, but as an indication to tell you exactly what your flow is, it's not as accurate as it could be. So it's always worth installing a flow meter. So in terms of accuracy, when we're talking about gas flow, there's no doubt about it that a flow meter is going to be far superior to a standard argon regulator. And I've tried a few, I've got a couple of others down here, and I got another new one as well. I've compared them to each other and they all differ wildly. And so without a doubt, you put one of these on, it's going to save you money. I mean, if it just saved you a third of the bottle on a 10-litre bottle, then it's going to pay for itself on the first bottle, isn't it? Why do we need gas when we're MIG welding? Well, the gas is often referred to as shielding gas, because what it's doing is it's shielding the welded area for that split second it takes the weld to set from oxidizing. Now you can use a light bulb as an analogy for this, because a light bulb is just basically a filament held within a vacuum. Filament being a simple coil of wire and the glass keeping the vacuum present, stopping the oxygen in the atmosphere from getting to the filament. So if I connect electricity to this bulb, the filament will glow white hot. What's stopping it from vaporizing is the complete lack of oxygen around it. So let's break the glass and see what happens. So this is what the wire feed unit, and this is the spool of wire, and there's some rollers in here, and these rollers push the wire through into the torch. So there's a nut on here if I wanted to change the size of wire, because it'll take 0.8 millimeters or 0.6 millimeters. So just undo this nut. I mean, a lot of welders are like this now. pull this off, and I'll get a close-up on this. So we're looking at the wire feed roller now, and you can see it's got 2 grooves in. The top one is what it's set up for now, which is 0.8 millimeters, and the bottom one is 6. If I wanted to use 0.6, what I have to do is pull this off, turn it round, and then put it back into the wire feed, and we'd be ready to go. But I use 0.8 most of the time, so I'll leave it as it is. And that is all you really have to do to convert it over from 0.8 to 0.6. You will have to change the contact tip in the end of the torch as well. So put that back on there, and I'll show you now how to set up the tension on the wire feed. To set up the tension on the wire feed, what you want to do really is loosen your adjustment right off, and then trap the wire. So the wire's pinched now, and we've got no tension on this at all. I've wound the tension all the way off. And then what we'll do is we'll turn the machine on. We want it so that if there's any reason the wire can't come out the end, whether it gets welded to the contact tip on the end, or it goes against a workpiece and it isn't arcing out properly, or you've got too much wire feeding, what you want it to do is slip. So I mean, I've got no tension on it at the moment, so it's going to slip ever so easy. So I'll turn the tension up a little bit. I won't give it too much, so I'll turn up the tension slightly. We should start to see it bite now, and then start spooling the wire through. There you go, it's working now. The wire's coming out the end, look. If I put this up against something now, like this wooden block, I want to be able to stop the wire from coming out. So you should stop that from spooling now. So it's slipping now on the rollers, it's not pushing the wire through at any cost. If I take the torch off this block, yeah, it's working absolutely fine. So this is absolutely fine the way it's set up. I will just put a little bit more tension on than it's got on now. Just make sure it's still, yeah, it's still slipping absolutely fine, which is what we want. So I've got this welder set up with 0.8 millimeters. I've got a brand new reel here of 0.6 millimeters, and I just got a tiny little offcut there. I don't know whether you'll be able to see the difference between the two just by looking at it as an image. They don't look too different to me on the camera, but there is quite a bit of difference actually. Now, for years and years I used 0.6, or I tried to persevere with 0.6. At the time, the welder that I was using, because I was only doing panel beating at the time as well, I wasn't sort of fabricating brackets or anything too much. And the welder I was using didn't have particularly great wire feed. Probably also had issues with the liner in my lance and torch. Probably not particularly the best. The wire feed was pretty ropey as well. What used to happen almost on a daily basis is the wire would buckle the other side of the roller, so the rollers would force the wire through, and for whatever reason there'd be a snag on the wire, like it had welded itself to the contact tip or something like that. And immediately, and it didn't matter what tension I had on the rollers, immediately it would buckle just in there and then all spool up inside of the machine. And out of total frustration, I changed over to 0.8 millimeters, and I never had the problem afterwards. And I soon got used to the difference as well. And what I have found as well with the 0.6 is if you do anything that's heavier, so you want to sort of weld a bracket up or something like that, you'll often find that the 0.6 doesn't seem to go anywhere. You seem to be welding away and not getting much build of weld coming out, and that's my experience anyway, and that's why I switched over to 0.8. Like I say, years and years ago, and I never sort of really looked back, to be quite honest with you. But having said that, with a decent welder, a decent setup and everything else, and without the issue of this buckling situation and the wire all spooling up inside the welder, the advantages of using 0.6 would certainly be, if you were just welding car bodywork all the time, then you would certainly be using lower amperage, because the wire's a lot thinner. I know there doesn't sound like a lot in it, but it is quite a bit thinner, 0.6, and therefore welding thinner materials could be quite an advantage if you're using 0.6, because lot less energy is going into actually melting the wire, and because there's a lot less energy going into melting the wire, then you're not going to get the heat distortion and you're not going to be putting as much heat into the panel. So it's a little bit of one of those situations, but like I said, I've used 0.8 and been very happy with it. Questions that have been put to me many times are, Trev, I don't understand when you were using your spot welder, so my single-sided spot welder, a lot of people ask this. Why is it you're not wearing any gloves? How come you're not getting electrocuted? I don't understand. Why have you got enough power there to make steel glow red and you're not dropping dead on the floor? I don't get it, Trev. Please explain more. And the other question as well, of course, is I keep watching these videos, Trev, on YouTube, and I keep reading forums, people arguing backwards and forwards, and I don't understand why they keep saying that when you turn the power up on a Mig welder, you're not actually turning the amps up, you're turning the voltage up, and that voltage has very little to play in the welding process. And all these questions are very hard to explain, and they're also extremely confusing, and in a way you don't really need to know any of the answers. But what I'll do is I'll give you the answer. The reason I say that is because you can weld perfectly well and not even know, you know, you can literally know how to plug the welder in, turn it on, turn the gas on, and you'll know from experience how to set the welder up, and you'll know that when you turn that dial to there, then it welds really well, and if you turn it too far, it stops welding, etc, etc. But for all those people that really want to know, then I'll try my best to put it across to you in terms differently from you've probably heard before. So I'm going to use a few metaphors and a few analogies, and I'm going to try not to go down the same road as all those other people that have made those videos that have confused you. I'll try and put it across in a way that you're going to kind of understand. So first things first, let's talk about electricity, because a lot of people have asked me, they say, well, people talk about volts and amps, I don't understand the difference. Well, let's start there. I've always been confused about things that I can't see. So when somebody's explaining electricity to me and they're just sort of giving it to me in the state that it is, you know, it's not a mechanical thing, is it? When you can see rods and levers and everything else, you can look at it and work out exactly how it's working. Electricity is a little bit harder because it's invisible, of course. So probably the best person that ever sort of explained things to me was my own dad, because my father, he used to be a technical author, so he would write manuals on how power stations work and how radio antenna work and things like that, you see. So he's quite a clever guy actually, and very serious chap. So certainly farting around the dinner table was definitely frowned upon. So anyway, I mean, when I was like a young kid, I'd be out sort of with me mum and dad, walk through the countryside, you know. It's probably like, this is going back about 40 years now, when I was a little kid. You're walking along, you say, hey, what's that little wire going across there? You know, there's these metal posts sticking up with these plastic sort of circular clips on the top and the wire passing through inside. My dad would say, that's an electric fence. That's keeping that horse in that field. The horse won't come out because the electric fence is there. I'm thinking to myself, how can a tiny little piece of wire like that keep that horse in that field? And you say, well, it's because if the horse touches it, he gets an electric shock. And he doesn't like the electric shock, so he doesn't go near the wire again, because he realises every time he goes near the wire, he gets an electric shock. So, you know what I'm going to say next. Of course, curiosity got the better of me. So, if I touch that wire then, Dad, what would happen? Well, they would give you an electric shock, son. Well, won't that kill me? No, it won't kill you, son. It'll just give you an electric shock. So, of course, curiosity got the better of me, didn't it? And I went over, and I reached my hand out. Holy! I let go of it, and my arm, it bumped all up my arm, and I felt absolutely dreadful. And I turned around to my dad, and I said, flipping heck, what was all that about? Well, what you felt there, son, was the force of 10,000 volts. 10,000 volts? How come it didn't kill me? Well, because there was very little amperage behind it. Then of course curiosity would get the better of me again, and I'd like, touch it again, do it again, do it again. Shall I touch it again, Dad? Well, yes, touch it again if you want, son, but no farting next time, okay? So that was my first introduction to electric and electric shocks. And, you know, you can have 10,000 volts and you can have many thousands of volts and it won't kill you. And yet, your household electricity, 220 volts in the UK, you touch that, you could drop dead. And it's because it's the volts amps combination, and amps can be divided into smaller divisions called milliamps. Now apparently 100 milliamps, which is 0.1 amp, so nowhere near an amp, but 0.1 amps, at around 40 volts plus, it could potentially kill you at just 40 volts, potentially, I say, if you were very unlucky. And that just goes to show how little amperage you actually need to stop your heart. When you consider the average car battery's got around 50 amps there, you know, but it's only 12 volts. And you need a certain amount of voltage to break the surface tension on your skin. So when we're talking about, like my little spot welder, I think it operates at something silly, absolutely ridiculous, something like 7 volts or something. So it's nowhere near the voltage required to actually get those amps into your system. So I use a few analogies to try and better explain volts and amps, and then I'll build upon that and I'll talk about the welder and how the welder uses volts and amps. Now I realise there are going to be lots and lots of holes in the theories that I'm going to be talking about, but the reason for that is because I'm trying to keep things as understandable and as simple as I possibly can. Let's talk about what electricity is. So we'll say this is an atom, and in the centre of an atom is a positively charged nucleus, and whizzing around the atom are negatively charged electrons. Now the electrons are attracted to the nucleus because they contain an opposite charge. They are repelled from each other because they contain the same negative charge. Everything is made of atoms, and let's just say for argument's sake that they stay in their fixed state. But when we're talking about certain metals, for example copper, the negatively charged electrons can become fluid by means of magnetism. Electricity is generated by passing a magnet through a coil of copper, and the electrons then become displaced to produce electricity. Here we have our displaced electrons. They're all negatively charged, as said, and they're all repelling each other. A little bit like they've all got a little spring pushing the other one away. When the electrons are pushed together, there's a tension in between them, and we call that tension high tension or high voltage. It's a pressure there. Often voltage is referred to as pressure. Electrical pressure is voltage. Here we have a line of electrons. Let's just say that they're all lined up along a wire and they're all moving. They want to move because of the pressure in between, because the pressure is pushing them apart, which causes them to move when they're in a circuit. Now let's talk a little bit about amps. So what we could say is this is a wire. There's a line of electrons moving along the wire, but there's not many electrons there. It's just a thin, weedy line of electrons. They're pushed tightly together, so it's extremely high voltage. But let's talk about amps quickly. So let's just say that the amount of electrons passing a static point for a certain amount of time could give us a representation of how many amps there are. So this picture could represent high voltage and very few amps. And this picture could represent lower voltage and low amps, because the electrons are spaced out further. Because there isn't the pressure in between the electrons, the desire to move isn't as strong. This picture could represent lower voltage and higher amps, because there's a lot of electrons passing by, but the pressure is very low in between the electrons. And in this picture we can see that there's a great deal of electrons and they're all tightly packed together. So this would represent high voltage and high amperage. Using water as an analogy for electricity can be a really useful tool when you're trying to get your head around how electricity works or the characteristics of electricity. So we've got two waterfalls, and both waterfalls are set at the same height. So the height from A to B on both waterfalls is just the same. The volume in this waterfall of water going down it is far larger than this one. So let's just focus on this one for a moment. So we've got a height difference from A to B, or a difference in potential, or pressure difference. So the pressure of the water coming down, the amount that it wants to move from A to B, would be the voltage, and the current or the volume of water passing this point, we could say, well, that's the amperage. And we could also say the combined work of the fall and the volume could be watts. So C would tell us where watts was, because watts is a combination of the voltage and the amperage times. So volts times amps gives you the watts. Interesting little tool aside from this is, if you know the voltage that you're working with, and a component like a light bulb has got watts written on the side. So say you put in a light bulb in your car, you knew your car was a 12 volt system and it said 65 watts on the light bulb. You know that if you divide 65 by 12, it's going to give you the amperage. So it works both ways. Now in this waterfall we've got very little water flowing down the waterfall, so this would represent something that was very, very high voltage, because we still got the fall. So we got the difference in potential, which is extremely high, but we haven't got much water flowing down there, so we haven't got many amps. So this would be low amps, high volts, high amps, to give you a representation of the differences. Again, we're talking a water analogy here, and if you haven't already worked it out, which I'm sure you have, we've got a difference in potential from A to B, and we've got water flowing down a river. The volume of water represents the amps, and the amount that that water wants to get from point A to point B would be the voltage, and the combined work of the two would be the wattage. So right there would be the part of the river that had its highest pressure and highest current. So as I said, the combination of the two could give you a watts calculation. And the same this side as well, got far less water running through this river. Although the fall is just the same, so the voltage would be just the same, we got far less amps going on here, but the same voltage in either scenario. I've made up this piece of apparatus so that we can use air pressure as an analogy for electricity. So this will simply connect to an airline and pressure it up with compressed air. Now I've got a pressure gauge on here so we can monitor the actual pressure coming out of there, because this is just a T-piece. So all these three exits are a junction, so this is the junction to all three exits, so the pressure will be exactly the same in here. And I've got these outlet ports, and one is a 2mm, so I've brazed the end up on this one and then drilled a 2mm hole through there, so that's 2mm, and this is a 5. So these two are going to represent amps. So whatever's flowing out of these will be the amperage, and as we said earlier, voltage is pressure, so we can actually measure the pressure on the gauge. So what I'm going to do is I'm going to set the pressure to around 2 bar, which is around 25 pounds per square inch, and I'm going to maintain that pressure using both outlets. Now what will happen is there will be a pressure drop when I change the outlet from the small one to the large one, but I can maintain that pressure by simply turning the air pressure up that enters this T-piece. Suspended from the ceiling of the garage, here's a big sheet of steel, and the outlet port is aimed directly at that sheet of steel. So when air comes out, so we could say that the air coming out, the airflow is the current, so we could say that that's amperage. So the more amps that comes out, the more that sheet is going to blow back. We're going to keep the pressure exactly the same, 2 bar on each outlet port. So this is the 2mm one. We're increasing the air pressure now up to 2 bar, and we can see the sheet leaning backwards. This is with the 5mm. We can see how much greater it is with the 5mm. No pressure at all. 2mm, 5mm. We can also use this as a useful analogy for a voltage drop. So as I'm unscrewing the outlet port, you will see that pressure drop. So like we say, we're using it as an analogy of the voltage. So as soon as the amps raise, so now we're drawing more amps. When we release the outlet port, more amps drawn, voltage drop. I'll screw the larger outlet port in now, so I'm screwing the 5mm one in, and we can see that the needle's just flickering up again, just to show that the voltage is rising as we reduce the amps. So let's build upon what we know, and then we can use this knowledge to have a greater understanding of what's actually happening when we're MIG welding. So voltage is electrical pressure. Voltage creates flow. With no voltage, there is no electrical flow. Nothing happens. The flow of voltage doesn't create heat. That's an interesting one, that one is, and that's something that a lot of people sort of struggle to get their head round, that the flow of voltage through an electrical component or along any wires, doesn't matter how much it is, it doesn't create any heat. And if you think about it, you know, there's high voltage systems like your HT leads on your car and the electric fence and all the rest of it, thousands and thousands of volts, no heat. And yet something like my little spot welder that only generates something around about 7 volts gets steel red hot. So the voltage doesn't play any part in generating the heat. All electrical components use or consume amps and create resistance. Resistance creates the heat. So it's the amps flowing through an electrical component. So wherever there's a component, there's resistance. Wherever there's resistance and amps, there's heat being generated. The more amps that are consumed, the more resistance, the more heat that is generated from that consumption. A voltage drop happens or occurs when current flows. So when amps flow, the voltage drops. So let's start talking about MIG welding. And let's briefly discuss what I'm not going to be talking about, because all these things obviously will probably have some part to play in power consumption, and maybe I'm oversimplifying things by leaving these out, but we could talk for days and days about each subject and still be completely hopelessly lost. And all this is about making things easier to understand. So let's not talk about the different modes of transfer. What I mean is how the MIG wire gets from here to here is the modes of transfer. So there's globular transfer, there's short circuit transfer, there's spray transfer, and there's pulse spray transfer. So let's just discount that. We know all about that, or we know about it. Let's just discount that. We're not talking about the thickness of the material we're welding. We're not talking about the diameter of the wire. Obviously, all these things will have an influence on power consumption. All I really want to talk about is wire speed and arc length, because they're very closely related, and I believe that these have the biggest influence over the amp consumption, and why you've got a voltage control and not an amp control, and why the wire speed controls the amps. So let's just talk about that. MIG welding power sources have what is known as a constant voltage output characteristic, often referred to as a CV. You often see that written, CV, constant voltage. Note the word characteristic. The arc voltage is established by setting the output voltage on the power supply. The power source will then supply sufficient welding current to melt the welding electrode at the rate required to maintain the preset voltage. This means that the wire feed speed can be used to control the welding current. As the wire feed speed is increased, the arc length will momentarily become shorter, so the arc voltage becomes lower than the preset value. Because of its output characteristic, the power source will supply a higher welding current. This increases the melting rate of the electrode, which self-corrects the arc voltage and the arc length. So let's go into a little bit more detail on that, and I'll give you another water analogy. So when we're talking about a constant voltage output characteristic, what we're talking about is setting the voltage to a certain voltage. So as I said in part 1, you set the voltage to the thickness of the material you're going to weld, or what you think it should be. So, you know, once you get experience, you can make a pretty good judgment decision on that. So you set the voltage to the thickness, then you match the wire speed to the voltage. So let's go a little deeper into these constant voltage characteristics. I'll try and fill it out with a little bit more information to try and make it a little bit more understandable. So let's just say, for argument's sake, let's just say you'll realise that you haven't got the welding speed high enough, so you budge the wire speed up. What instantly happens? So say you're actually in the process of welding and you just crank the welding wire speed up slightly. What's going to happen is the arc length is going to get shorter. So the last picture showed a long arc length. This picture is showing a short arc length. So what happens is you turn the wire speed up, the wire comes out, and it makes the arc length shorter because you've got more wire spooling out, more wire obviously creating more resistance. You've got the voltage set to a certain voltage, and what happens is you then put the arc under pressure to perform. So it's having to work harder to maintain a shorter arc. Now all this happens in a fraction of a second, so you'd be unaware of it. But what this is the constant voltage regulating the arc length, because welding is all about sustaining the correct arc length. If we haven't got a correct arc length, then we're not welding properly. And all this is all about is it's about maintaining a stable arc. So when current flows, there's a voltage drop. Now we're on the characteristics, so we talked about the constant voltage characteristics. Now we can use a good analogy here for water again. So think about a hose pipe running. So we've got a hose pipe running and water's just coming out the end, and there's very little pressure there because there's nothing stopping that water from coming out. So we could say that that would be a very, very low voltage, high amperage system. So we've got good flow coming out the end, but there's not a great deal of pressure to it. Now, utilising the electrical energy that's there, we can convert amps into volts and volts into amps. And we can convert those amps into volts by increasing the electrical pressure. We increase the electrical pressure, we put our end over the hose pipe, we are converting the same water supply, so we've got the same volume of water. When we put our thumb over the end, we create more pressure. The pressure increases to raise the voltage, and the amps drop in relation to the voltage rising. And same goes the other way round. When the voltage drops, so we release our thumb slightly from the end of the hose pipe, so the pressure drops, but we've got a greater flow, so a greater volume of water is coming through. And this is kind of how a constant voltage power supply would work. What would happen is the voltage would drop, and naturally the current would rise, or the available amps would rise, probably a better terminology. So the availability of amps will rise when the voltage drops, because we've got more amps there. Then there's more amps there to melt the wire back. The wire melts back to the appropriate arc length, maintaining the arc length, and that's how a constant voltage power supply works, or an analogy of how it works to try and make it more understandable. Looking at the situation from the other side, if we reduce the wire speed, what also happens is, of course, the arc length becomes a lot longer, and the constant voltage again rectifies the problem by delivering less amperage there. And so less amperage means that the wire stick out a little bit further, maintaining the arc length of gain. One little thing I'll just chuck in as a bit of a bonus, I wasn't going to say this: if you increase the distance of the wire between the shroud and the workpiece, that is increasing the stick out, it's called. And what will happen is there'll be more resistance created in the wire, because you're making the wire longer from the contact tip, because that's the contact tip. That's where the wire is earthing there. So you've got the two electrodes which would be there to there, and what you're doing is you're increasing the electrode length by pulling the torch back, increasing the resistance because you've got more wire there, and that will actually result in a cooler weld if you're welding very thin material. So if you're blowing holes through, just try pulling the torch back a little bit, and you will notice that you will stop blowing holes as easy, rather than just messing with the controls on the welder. That's something else you can do. I believe at far higher voltages, I believe the opposite is true, and you actually get better penetration on thick materials, because what happens is you increase the stick out, that stick out gets hot, so it gets softer before it goes into the weld pool. But I'm all about thin stuff, so like I say, if you pull it back welding thin stuff, you will notice that you will get less heat on your weld, because the stick out is absorbing some of those amps. Before I wrap this video up, I ought to just say before I go, because somebody else will make that valid comment, that indeed you do need to have the voltage dial set to something in order to actually produce the amps, to produce the heat to do the welding. It is indeed a correlation between what you set the voltage dial to and what you set the wire speed to that generates those amps needed. And that would be a very valid comment to be made. If there's no voltage, there's no electrical flow. If there's no electrical flow, there's no electricity. Well, thanks very much for watching, and I really hope you got something out of that. I was sent an email the other day, and a viewer sort of picked up on a really good point from part 2, because they asked me the question about MIG welding versus TIG welding, or the difference between the two, and they kind of were saying, was I saying in my video that you should TIG weld every single butt joint and never use a MIG welder again? Well, that wasn't exactly what I was saying, and wasn't exactly the point I was trying to make. The problem with doing these videos is you've got to keep things brief while giving, you know, as much information as you can. The problem is if you give all the information and cover all bases, all you get is nothing but complaints about the videos going on for too long. So you've got to try and sort of toss up the balance between keeping it brief and interesting and giving all the information you want to put across. It's not an easy job to do. Anyway, I would say that I would probably TIG weld probably 90–95% of all my butt joints now. The reason I sort of do this is because obviously it makes a nicer job. The reason I would still use a MIG welder is because in certain cases I can still make a colder joint using a MIG welder than I can using a TIG welder. I'll sort of try and give you a sort of fuller explanation. So about, I don't know, 3 or 4 years ago, I was doing a complete windscreen aperture repair, so all the way around the windscreen, including the roof. Now if you imagine, I was welding all the way across the roof, a sort of 2.5, 3 inch sort of wide section. So right from where the windscreen would be, start right up into the roof, about 2.5, 3 inches back, all the way along. So we're talking a joint that long, on the most flexible and weakest part of the whole of the car, right across the roof. Now, if you've welded anything, you'll be able to appreciate how much heat distortion that would create doing that, and it's the kind of thing you could do and almost write a car off if you didn't get it right. So using my heat sink method, where I use some wet towels and just spot it with a welder, I was managed to MIG weld that sort of repair section in with creating hardly any distortion whatsoever. Now, the reason I did this was because I had no access underneath. There was all strengtheners, there was an inner panel, there's all strengtheners inside the roof. The only other way you could have approached something like this would be to completely remove the whole roof, but then of course you have to balance up. Are you going to ruin the car by taking the roof off? You know, what damage are you going to create by taking the whole panel off? Sometimes you can take a complete panel off, then do a rust repair, and then weld it back on, and weld it back on in a way that manufacturer would have welded it back on, because we're sort of welding joints in which were never there before, of course, because we're doing rust repairs. So we're always kind of jointing things where they shouldn't be, you know, places where you're going to create the most amount of heat distortion. So getting back to the whole welding side of things, if I was going to TIG weld that on with no access from behind, because when you TIG weld, really you need access to get a dolly up behind and planish the weld out, so you stretch it back out, and that gets rid of the heat distortion, or most of the heat distortion anyway. Well, not being able to do that, I just kind of thought, well, I'm just going to MIG weld this. I would have preferred to have TIG welded it, but I know I would have made a mess of it, because when you TIG weld something, of course, you've got to open it up for that dwell period of time to be able to create a weld pool and do a little run. Even if you kept it to a tiny little run like that, you're still going to create quite a lot of heat in comparison to just giving it a spot of MIG, letting it completely cool off, doing another spot over here, letting it completely cool off, and using the heat sink. Now, like I was saying, it's wildly varying and dynamic. Yes, you will make that steel ever so slightly more brittle by force cooling it down like that, because you've essentially taken something that's very, very hot, you got something that's very, very cool right next to it, so it's wicking the heat out of that panel work around. It will cause that steel to be very slightly more brittle than it would have been if you'd have just MIG welded it without the heat sink on there. But like I say, you've got to weigh these things up. What would you rather? Would you rather it be slightly more brittle but without the need to have 2 inches of filler put on the top to try and get rid of all the heat distortion? And this is the kind of thing that we're always up against. It's always a fine balance between what's the best thing to do. All these types of welding and all these variations of welding, they all have their plus points and their minus points, and you've got to evaluate each welding project separately. You know, what you did in one place and it turned out perfectly, you got to do it somewhere else and it's a complete disaster. And it's because the panel is going to behave in a different way depending on the structure and the shape of the panel. You know, if it's right near a detail line like a swage line and you weld something close to that swage line, that's going to have far more strength in it and resist warping more than something right in the centre of a very low crown, you know, almost flat panel. That's going to be the hardest kind of, you know, welding repair that you can do, right in the centre of a flat panel. And the common mistake that everyone makes when they sort of start off down this road of restoration is you're making up your repair panels, and you know, say you've got 2 inches of rust in the bottom of a door or something, and so you just make a 2-inch repair. You know, you just sort of make something that just covers it, and then you find that the steel's just perforated a little bit further up, so you're kicking yourself because you didn't make it an inch taller. So then you make it an inch taller, and then you get horrific distortion down the whole thing because you're right in the centre of the panel where there's no strength. And then you sort of learn that, well, if I extended that panel by another 4 inches, so you're almost replacing 4 inches of good steel, and you're thinking to yourself, well, this is absolutely crazy, why would you be doing that? Well, 4 inches up, there's a swage line in the panel, and that helps stop all that distortion. So you sort of learn after a while. You don't make it 2 inches, you don't make it 3 inches, you now make it 7 inches, you know. So you go from 2 to 7 inches, and you got no heat distortion. And it's these kinds of things that you go through, and it's an experiential thing, and you've just got to make lots of mistakes and overcome those mistakes to sort of work out what's the best way. It all comes from experience, which is extremely hard to teach people experience. Anyway, I'm going to wrap this up. Just say briefly that I do have some more hammers in stock. Please don't ask me in the comments section the link to the new Trev's Blog shop, because I don't have it yet. There is a Trev's Blog shop coming up very shortly, and I'd just like to say a huge thanks to Rob from Extreme Engineering. So Rob's helped me out with some mugs and some t-shirts also, so he's going to be taking care of those for me, or certainly helping me with them anyway. Thanks very much for that, Rob. I'll put a video on in the next couple of days. Hopefully the shop will be up and running then. I have some hammers for sale, some mugs, some t-shirts, and some little toolbox stickers. So anyway, until then, I have to say bye for now.